Welcome everyone. I am so thrilled to have you joining us today for a brand new deep dive.
Yeah, it's great to be here.
We are going to be looking at something that is, quite frankly, hiding right in plain sight. We're going to explore these massive, unseen mechanical beasts that are quietly powering, well, virtually all of global trade.
It's a massive topic, literally.
Exactly. I'm talking about marine crosshead diesel engines. If you have ever looked out at a port or seen a cargo ship out on the horizon and wondered exactly what it takes to push hundreds of thousands of tons of steel across a volatile ocean, you are in the perfect place.
It's a topic that feels like it should just be about, sheer scale and brute force. When we imagine these ships, we picture heavy metal and massive
Right,
smokestacks.
just these big, dumb iron giants.
Yeah, but the reality operating below the deck is so much more intricate and honestly, so much more fragile than anyone realizes.
To guide us on this journey, we have an incredible stack of research on the table today. Our focal point, the anchor for this entire deep dive, is a really comprehensive presentation from March 2026.
Authored by Samad Tawfiq.
Right, from the Arab Academy for Science, Technology, and Maritime Transport. But to truly grasp the magnitude of where engine technology stands in that 2026 research, we're also pulling from a rich archive of scientific abstracts spanning back to 1983.
Because having that historical lens is vital. By tracing these specific leaps in engineering over the decades, we can see the exact trajectory of how these machines have been relentlessly optimized.
Optimized just to survive modern demands, really.
Yeah.
Which brings us to our mission for you today. We want to explore how these giant engines have evolved over the decades.
And we aren't just looking at the big, obvious metal parts.
No, we are diving into the microscopic, highly precise innovations, the chemistry, the lubrication, and the physical engineering that keeps global supply chains from grinding to an absolute halt.
It's a delicate balance.
It really is. But before we get into the timeline, I want to clarify something foundational. We keep using the term crosshead diesel engine. For anyone listening who is, say, only familiar with the engine inside their Honda Civic, what actually makes a marine crosshead engine different?
The difference really comes down to managing unimaginable scale and physics. In a standard car engine, the piston goes up and down inside the cylinder, right?
Yeah.
And it's connected directly to the crankshaft by a rod. As that crankshaft spins, the rod pushes and pulls at an angle.
Which naturally forces the piston to scrape sideways against the cylinder wall.
Exactly. Now, in a small car engine, oil manages that friction just fine. But in a massive cargo ship, where the pistons can literally be the size of a small room, that sideways force would tear the engine apart.
Just absolutely rip it to shreds.
Yeah. So a crosshead is essentially an extra mechanical joint. It sits below the piston and absorbs all that sideways lateral force.
Meaning the massive piston rod moves perfectly strictly straight up and down inside the cylinder.
Right. It's an ingenious piece of architecture designed specifically to manage heavy-duty wear and tear.
Okay, let's unpack this, starting with our 2026 anchor from Samad Tawfiq. Because this presentation really sets the stage for what these engines have become today.
It paints a picture of modern marine engines not as brute force iron, but as highly sensitive ecosystems.
The Tawfiq presentation brilliantly outlines the current state of affairs. In 2026, a marine crosshead diesel engine is expected to do the impossible.
Produce tens of thousands of horsepower.
Run continuously for weeks on end without a single misfire.
Operate on incredibly tight fuel budgets.
And do it all while strictly adhering to severe international emission standards. It's no longer just a mechanical device.
It's a precarious balancing act. If one single element, be it the timing, the temperature, or the chemistry of the lubricants, is off by even a fraction, the entire system is compromised.
Which makes perfect sense when you look at how much effort has gone into perfecting those tiny fractions over the years. To see how we achieve the sophisticated engines Tawfiq describes in 2026, we have to look back at the literal lifeblood of these machines.
Now we have to talk about the oil.
Yes, you cannot fundamentally change how an engine operates without completely revolutionizing the oil that stops it from tearing itself apart.
That's a great way to put it.
Let's look at this study from January 2009 by Shigeki Takashima and Nozomi Arumoto. They zero in on a major shift that happened right around the end of the 1990s and into the early 2000s.
Engine manufacturers were heavily pushing for high-output, high-efficiency engines.
And the researchers note that as the physical hardware changed, the chemistry of the oil had to transform along with it. But it wasn't just the engines getting more powerful.
The real catalyst for this chemical shift was environmental regulations, specifically the mandate to use low-sulfur fuels.
Wait, let me make sure I'm fully following this. The regulations say ships have to stop polluting the air with sulfur. That makes total sense to me. But the study implies that removing sulfur from the fuel somehow created a massive problem for the oil inside the engine. Why does the oil care if the fuel is cleaner?
It's a brilliant paradox of engineering. When a ship burns traditional heavy fuel with a high sulfur content, the combustion process inevitably creates highly acidic byproducts inside the cylinder.
And left alone, that acid would just corrode and eat away at the massive metal components.
To fight this, historically, engineers used a high base number cylinder oil. The base refers to the oil's alkalinity, its chemical ability to neutralize those harmful acids.
So it was essentially loaded with alkaline additives to act as a chemical shield.
Exactly.
So the oil wasn't just making things slippery, it was actively fighting a chemical war against the acid created by the sulfur.
Precisely. Now imagine you are an oil chemist in the late 1990s. The environmental regulations drop, forcing the shipping industry to switch to low sulfur fuels.
Meaning the engine is no longer producing all that intense acid.
Right. And if you keep pumping in that traditional, highly alkaline, high base number oil, you now have an excess of alkalinity with no acid to fight.
Oh, wow.
That imbalance causes its own severe deposit issues and engine wear. The regulations completely upended the chemical environment of the cylinder.
So the industry desperately needed a new low base number oil.
I see.
So you just take the alkaline additives out of the oil recipe and you're good to go, right?
If only it were that simple. Removing the alkaline additives fundamentally changes the structural integrity of the oil.
Because the oil still has to perform its primary brutal job, protecting a massive, multi-ton metal piston firing under unimaginable heat and pressure.
The true triumph highlighted in this 2009 research is how the oil suppliers managed to formulate these new low base number oils without losing any performance.
And the study actually quantifies that performance, and the numbers are wild. Over just a 10-year span comparing formulations, the suppliers managed to improve the high-temperature extreme pressure properties.
And the detergency.
Right, the detergency of their high base number oils by a massive 20 degrees Celsius. Now, I get the temperature part. Surviving an extra 20 degrees of explosive heat without breaking down is huge.
Yeah, it's significant.
But the study heavily emphasizes detergency. Why does a cargo ship engine need detergent? Are we trying to wash the cylinders?
In a way, yes. When we talk about detergency in engine oils, we are talking about the oil's ability to keep the internal metal surfaces completely clean of soot, sludge, and carbon deposits.
Because when fuel burns, it leaves behind sticky, abrasive residue.
Exactly. If that residue builds up on the piston rings or the cylinder liner, it acts like sandpaper, grinding the engine down from the inside out.
So improving detergency by 20 degrees Celsius means the oil can effectively wash away those highly abrasive deposits, even when the engine is running significantly hotter.
Yes. And the researchers note that the newer low base number cylinder oils, the ones developed to meet those strict environmental regulations after the year 2000, actually managed to achieve equivalent performance.
They match that extreme temperature stability and that intense cleaning power of the older, heavily alkaline oils. It's a massive chemical victory.
What's fascinating here is how chemistry had to act as the silent bridge between environmental policy and heavy industrial engineering.
Without those chemists figuring out how to balance the alkalinity while maintaining thermal stability, the entire push for low sulfur shipping would have stalled.
The engines simply would have destroyed themselves.
Yeah, incredible. But as we move forward in the timeline, the innovation shifts from chemistry to microscopic precision. Let's move out of the late 2000s and jump to 2019.
A huge year for this technology.
We're looking at a breakthrough paper by Yuhai He, Pailan Zhu, and their colleagues. They outlined the design and development of a brand new electronically controlled cylinder lubrication system.
Built to totally replace conventional mechanical lubrication.
To appreciate this leap, you have to understand the old mechanical systems. For decades, lubricating a marine engine was a relatively blunt process, wasn't it?
Very blunt. You had a mechanical lubricator tied to the physical rotation of the engine. As the gears turned, cams would physically pump and splash oil into the cylinder.
It was reliable because it was simple.
But highly inefficient. It essentially just sprayed oil in the general vicinity of the moving parts and hoped for the best.
The 2019 study introduces the electronic replacement, and I am looking at the data on this new injector. The numbers are just hard to wrap my head around, considering we're talking about a machine the size of a building.
They are extreme metrics.
It notes the oil injection pressure is operating at about 3.0 megapascals. Can you translate that into something I can actually picture? What does 3.0 megapascals feel like inside a cylinder?
To visualize 3.0 megapascals, imagine the intense physical force of a high-powered commercial fire hose.
Okay, I can picture that.
Now, take all of that aggressive pushing energy and amplify it, concentrating it down into a highly focused stream the size of a pinhead.
Wow.
It is an incredibly violent, high-velocity burst of oil designed to punch through the chaotic, pressurized environment of a firing engine block.
That paints quite the picture. And it's not just the pressure, it's the timing. The study lists the oil injection duration at 15 degrees of crank angle or less with a timing precision of 0.1 milliseconds.
Extremely fast.
I know a millisecond is a thousandth of a second, so we are talking about a 10,000th of a second precision.
Right.
But what does 15 degrees of crank angle mean in terms of how the engine is operating?
The crank angle is simply a way of measuring the rotation of the engine's main shaft. A full rotation is a 360-degree circle.
It makes sense.
When they say the injection duration is 15 degrees of crank angle, they mean the oil is only spraying for the tiny fraction of time it takes for that massive shaft to rotate just 15 degrees out of 360.
It's a fleeting, almost imperceptible window.
Exactly.
So instead of a mechanical pump just splashing oil around continuously, this electronic system acts like a microscopic sniper.
Yes.
It waits for the absolute perfect 10,000th of a second and fires a high-velocity burst of oil exactly onto the piston rings right as they pass the injector.
The efficiency gain from that pinpoint accuracy is staggering. It ensures absolute, perfect lubrication and acid neutralization exactly where the metal needs it most.
Without wasting a single drop of oil in the empty space of the cylinder.
But it goes much further than just being fast. The 2019 system is actively intelligent.
The research highlights how this new system actively regulates the oil injection frequency based on real-time factors. It isn't just firing blindly on a timer.
It's continuously reading the environment. It calculates the current load the engine is bearing. It factors in the specific sulfur content of the fuel currently flowing into the chamber.
It reads the total base number of the cylinder oil waiting in the tank.
It even adjusts for what engineers call the running-in condition of the cylinder liner.
Meaning the computer actually knows if the massive metal parts are brand new and still roughly wearing into each other, or if they are 10 years old and fully smoothed out.
And it alters the volume of oil accordingly.
It's a giant brain constantly managing these microscopic, high-pressure injections. And for you listening, if you are wondering about the actual business reality of a system this complex, the 2019 results are undeniable.
The numbers speak for themselves.
Because of all this targeted, highly regulated precision, shipping operators saw their cylinder oil consumption rate plummet by approximately 25%. A quarter of their oil costs just vanished because they stopped wasting it.
Which fundamentally changes the economics of running a global fleet. The savings are so profound that the system was incredibly successful as a commercial retrofit.
The researchers note it was installed onto more than 120 main engines already in service on the water.
With the operators seeing a complete financial payback on the upgrade in less than 2 years, it's a flawless example of theoretical engineering achieving total success in the practical world.
Here's where it gets really interesting, because engineering isn't always a flawless transition from the chalkboard to the ocean. What happens when our perfect mathematical models hit the messy, unforgiving reality of real-world physics?
That brings us to the humbling investigation from 2008.
Yes, let's look at this paper by Masaki Tanaka and Takashi Kawada. The focus of their study is the deformation of a cylinder liner used in large Crosshead diesel engines.
Deformation basically means how these massive pieces of metal warp, bend, and distort under the extreme stress and heat of operation.
Knowing exactly how that metal will expand and distort is the holy grail of engine design, isn't it?
Absolutely. If you know exactly how the cylinder will warp when it gets hot, you can design the piston to fit perfectly into that warped shape.
To figure this out, engineers heavily rely on highly complex mathematical and computational models to predict the metal's behavior before they ever build the engine.
Right.
So Tanaka and Kawada did something very straightforward, but incredibly revealing. They calculated what the theoretical deformation of the cylinder liner should be based on all their advanced math.
And then they went out and physically measured the actual deformation of a real cylinder liner while it was operating.
And the results. The phrasing in the academic paper is so polite. They stated the mathematical predictions and the real-world measurements were, quote, not perfectly coincidental.
A wonderfully diplomatic way of saying their math failed.
Utterly failed.
The engine was entirely refusing to behave the way the computational models dictated it should.
Not perfectly coincidental. The researchers dug into the discrepancy to figure out why the math failed, and they found 3 specific culprits throwing off their models.
If we connect this to the bigger picture of how we design machinery, this failure is a brilliant lesson in the limitations of our own assumptions.
The text identifies the first reason as oversimplification. The engineers applied what is known as an axis symmetrical model to a cylinder block that is, in physical reality, a highly complicated asymmetrical shape.
Yes.
To make sure I'm visualizing this correctly, is it kind of like trying to calculate how a jagged, lopsided rock is going to bounce down a hill, but to make the physics equation easier to solve on paper, you just assume the rock is a perfectly smooth sphere?
That is the perfect analogy. Your math might be flawless for a sphere, but in reality, that jagged rock is going to kick off the dirt in ways your simplified model completely missed.
So to the computational model, treating the massive metal cylinder as a perfectly symmetrical tube makes the math elegant.
But a real marine diesel cylinder block is covered in cooling jackets, fuel injection ports, and exhaust valves. It has thick parts and thin parts. It is structurally complex, and treating it as a simple shape completely ruined their calculations.
The second reason they identified was inaccurate temperature distribution, meaning the heat wasn't spreading evenly.
Exactly. Theoretical models often assume heat radiates somewhat uniformly. But inside a firing engine, the combustion process creates a chaotic thermal landscape.
So one side of the massive metal block might be experiencing vastly different temperatures than the other side simultaneously.
And this non-uniform heat drastically changes exactly how and where the metal warps.
And the third culprit destroying their math.
Improper modeling of the contact surfaces. The way the massive multi-ton metal components actually press, push, and rub against each other under the extreme stress of operation was not properly represented in their theoretical calculations.
The friction and pressure points were entirely wrong.
Entirely wrong.
It's such a profound takeaway. It perfectly illustrates that even in highly advanced marine engineering armed with supercomputers, the physical reality of a complex engine block will absolutely defy simplified math.
The metal is going to do what the metal wants to do, dictated by the raw physics of heat and pressure, regardless of what the spreadsheet says.
It forces a necessary humility. You cannot simply design a marine Crosshead diesel engine on a screen and assume victory.
You have to physically measure the true deformation. You have to respect the tangible physical reality of the machine.
So what does this all mean? We have covered a massive amount of ground today. We started with Dr. Sameh Tawfiq's 2026 presentation as our map pin, showing us the incredibly sensitive, highly optimized state of modern marine engines.
And from there, we looked back into the archives to see the specific battles fought to get here.
We saw the profound chemical evolutions cataloged in 2009, where chemists achieved a 20 degrees Celsius jump in detergency just to keep engines from destroying themselves on low-sulfur fuels.
We explored the massive technological leap in 2019, leaving behind blunt mechanical splashing for intelligent 0.1 millisecond electronic injections that conserved 25% of a ship's oil.
And finally, we grounded ourselves in the 2008 deformation study, witnessing the constant, humbling battle between elegant theoretical models and the chaotic warping of actual physical metal.
It really is a remarkable chronicle of human ingenuity and relentless problem solving.
It is.
And I think the real takeaway for you listening is this. The next time you look out at a port or you see a massive cargo ship slowly pushing across the horizon, do not just think of it as a huge, lumbering hunk of floating metal.
The sheer scale of those ships is deceptive.
Because beneath the deck, driving that massive weight forward, is a delicate, perfectly timed symphony. It is an absolute masterpiece of extreme pressure, continuously evolving chemistry, and intricate geometry operating in fractions of a millisecond.
It completely changes how you view the global supply chain.
Yeah.
The things keeping our world connected aren't just big, they are astonishingly precise.
And this raises an important question, something for you to think about as we wrap up today's journey.
Oh, absolutely.
We know from the 2008 study that traditional computational models heavily struggle to predict the physical warping of complex engine blocks under extreme heat. And we know from the 2026 research that the demands on these engines are only getting more intense.
So think about the tools we have currently developing.
Exactly. If traditional math failed to capture the chaotic heat and asymmetrical geometry of these cylinders, will the recent explosion of artificial intelligence and machine learning finally bridge that gap?
Could an AI model, trained on decades of real-world physical deformation data, finally allow engineers to perfectly predict and design the extreme, hyper-efficient engines of tomorrow before a single piece of metal is ever poured? A brilliant and incredibly timely question to leave you with. It is a stark reminder that innovation in this space is never truly finished. There's always a new tool waiting to solve an old limitation.
Well said.
Thank you so much for taking the time to join us on this deep dive today. We hope you walk away with a brand new appreciation for the unseen, microscopic precision powering our massive world. Keep asking questions, keep looking deeper, and we will catch you on the next deep dive.